Welcome to World Explain. Imagine, just for a moment, gazing down into a dark, churning abyss. It's the 1930s, and right beneath you lies a jagged underwater graveyard, swept by violent, freezing currents. To your left, there's a sheer, rocky coastline. To your right, another. And between them lies a massive void that the absolute greatest minds of the era say can never, ever be crossed. A void that has swallowed ships whole and shattered countless dreams. Today, in this explainer, we're exploring one of the most incredible, death-defying megaprojects ever attempted by humanity, and we'll uncover the brilliant minds who literally risked everything to conquer it. I mean, just look at the sheer, terrifying hostility of this environment. We aren't just talking about crossing a wide river here. This is the Golden Gate. It's the violent mouth of the Pacific Ocean. It's a 2.7-kilometer expanse defined by blinding, freezing fog and winds so incredibly violent they could effortlessly tear a man right off a scaffold. The tidal currents surging beneath the surface are so unimaginably powerful they could instantly crush conventional structures. It's essentially a deadly void, a natural fortress guarding the San Francisco Bay that relentlessly fights against any human intrusion. So, let's get right into part one, an impossible engineering dream defying the void. This is where Chief Engineer Joseph Strauss enters the picture. And you have to understand, he didn't just see a construction project, he saw a life or death battle against nature itself. Facing a very loud chorus of critics who declared bridging this gap totally impossible, Strauss had to outsmart the ocean. To really grasp his genius, we need to look at why conventional ideas would trigger a catastrophic failure here. Sinking massive concrete piers for a standard beam bridge into 300 feet of violent water, that would be a complete financial nightmare, and it would permanently block massive ships from entering the bay. On the flip side, an arch bridge would let those ships pass, sure, but to span this mind-boggling distance, the arch would have to be built so impossibly high that it would inevitably collapse under the sheer weight of its own ambition. There was simply no margin for error. Okay, let's dive into this. Faced with these absolutely disastrous limitations, Strauss chose an incredibly elegant solution: the suspension bridge. In this absolute masterclass of engineering, the crushing weight of the concrete road deck doesn't actually push down onto pillars from below like you might expect. Instead, it's hung entirely from the sky. It's suspended by vertical steel cables, which are attached to massive sweeping parabolic main cables strung between two giant towers. It essentially becomes this beautiful, sweeping arc of pure tension, safely carrying thousands of tons of weight completely over those deadly currents below. But let's take a second to truly absorb this number: 2.7 kilometers. Spanning this awe-inspiring distance with a road deck floating over the violent Pacific is mathematically staggering. The main cables have to support an unimaginably huge weight over a vast, totally empty space. And when you hang thousands of tons of steel and concrete over 2.7 kilometers, you birth an invisible, terrifying enemy. That enemy is tensile load. Which brings us to this absolutely terrifying physics puzzle. The massive main cables are pulling inward with an incomprehensible amount of force. If you simply string a cable between two towers and hang a heavy bridge from it, that unbalanced horizontal tension will literally pull those massive steel towers inward. The towers would physically bow, the cables would snap like brittle string, and the whole bridge would meet a premature, catastrophic death in the icy waters below. So the ultimate question is, how do you stop millions of pounds of steel from ripping itself apart? Well, the answer starts by anchoring the main cables deep into the earth on either shore. But then you face a brand new dilemma: the actual height of the towers. Imagine a really high-stakes physics experiment. If you build short towers, the angle of the main cable is really shallow. That induces a massive, violent amount of tension, so much that a short tower design will violently snap. But if you try to build ultra-tall pillars to steepen the angle and relieve that tension, the sheer financial cost of the materials becomes an absolute impossibility. You're trapped between physics and finance. Strauss needed a miracle of mathematics. He needed a perfect equilibrium between catastrophic failure and complete financial ruin. And he found it in the number 746. By calculating the exact optimal height of 746 feet for his towers, Strauss found the ultimate compromise. He allowed the massive main cables to carry the exact right amount of tension without snapping, while keeping the towers just low enough to remain economically feasible to actually build. It was just a brilliant masterstroke of calculation. Moving on to part two, defeating the invisible killers, thermal expansion, and brittle concrete. You see, conquering the massive physics of the towers was really only the beginning of the battle. As blueprints started becoming reality, Strauss had to face relentless ticking clock threats, the kinds of things that destroy megastructures with microscopic stress over time. The first invisible killer was the connection crisis. If Strauss had directly connected the vertical steel suspenders to the concrete road deck, the bridge would have undoubtedly failed. Concrete is deeply, inherently brittle under tension. The relentless pulling would quietly fracture it until the road simply gave way and fell into the sea. So Strauss's solution? A really complex, heavy-duty steel-to-steel truss system. The steel suspenders hold the steel truss, and the concrete road simply rests safely and securely on top. Yet the second invisible killer was even more insidious, and it was hiding in plain sight: the sun. As the blazing California sun beats down on the structure, extreme heat silently expands the metal and concrete. If this entire 2.7-kilometer megastructure were built as one solid rigid piece, it would swell, warp, and literally tear itself apart from the inside out. The thermal expansion would cause massive, unstoppable stress on the towers and catastrophic damage to the roadway itself. And this brilliantly illustrates Strauss's absolute genius. He deliberately divided the massive road deck into 7 completely separate pieces, leaving terrifying, gaping gaps between them. To bridge those gaps safely, he installed finger expansion joints, these intricate interlocking steel teeth that slide past one another. During a hot, scorching day, the road deck actually grows, and these joints slide by almost 4 entire feet. The bridge literally breathes. And because steel expands faster than concrete, he went ahead and added tiny expansion joints every 50 feet, ensuring the road never destroys itself. It's just phenomenal engineering. Which brings us to part 3, conquering the deadly Pacific, the South Tower descent. With the blueprints finally perfected, the physical war actually began. And nowhere was this war more incredibly dangerous than out in the deep, violent waters where the South Tower had to be built. The bedrock was buried 50 feet below the murky seabed. This wasn't standard construction. It was essentially a tactical military operation. Step 1. Immensely brave divers descended into the pitch-black, crushing currents to plant underwater explosives, blasting away rock just to create a flat surface. Step 2. They built massive concrete barriers called fender walls to deflect the deadly swirling tides. And step 3, honestly the most terrifying of all, under a thick reinforced concrete slab, workers continually dug out the seabed from inside, allowing the entire protective structure to slowly, painstakingly sink until it finally hit pure, solid bedrock. Once that completely impossible foundation was secured, the towers began their magical rise into the sky. But they weren't solid blocks of metal. Strauss designed immense, hollow steel cells. Fabricated off-site, these cells were shipped in and meticulously riveted together like gigantic, deadly puzzle pieces hundreds of feet up in the air. This cellular design provided extreme economy, saving them millions of pounds of expensive steel while still delivering the absolute mind-bending strength required to hold up the sky. Let's look at part 4, spinning the steel web, 27,000 wires. Next, the whole project moved from those crushing underwater depths to dizzying, terrifying heights. Just imagine for a second, balancing on violently swaying catwalks, completely engulfed in freezing fog, with the roaring ocean a massive drop below you. To hold up this megastructure, these workers consumed a staggering 129,000 kilometers of steel wire. Stop and really think about that. 129,000 kilometers. That is literally enough wire to wrap entirely around the Earth's equator, more than 3 times over. And every single inch of it had to be woven by hand up in the sky. So the crucial point is, how do you actually transform tiny wires into massive, unbreakable cables? Well, workers balanced on those narrow catwalks while a traveling spinning wheel zipped back and forth between the towers, pulling just a single wire at a time. Laborers manually grabbed these wires, passed them over towering saddles, and carefully clamped them down. Once 27,000 individual wires were bundled together, they used a massive hydraulic press to forcefully crush them into one single gigantic, hyperdense cable, which they then tightly sealed in galvanized steel to protect it from the elements. And that takes us to part 5, the ultimate stress test, the 50th anniversary. Fast forward half a century. The Golden Gate Bridge stands as a definitive global icon. But on its 50th anniversary, the bridge faced its most terrifying and completely unexpected physical threat, an event that pushed Strauss's mathematics to the absolute brink of disaster.
On that day, a massive, uncoordinated crush of 300,000 pedestrians flooded onto the road deck all at once to celebrate. The human body, as we know, is mostly water, and water is incredibly heavy. Standing shoulder to shoulder like that, they created a massive, highly concentrated dead weight overload that went far, far beyond anything Strauss had ever calculated for standard vehicle traffic.
Under this crushing, totally unprecedented weight, the physics of the bridge began to dangerously warp. The immense tension pulling on the main cables absolutely skyrocketed. That terrifying, unbalanced horizontal force we talked about earlier, it completely reared its head, and the massive 746-foot steel towers actually physically bent inward. The beautiful, sweeping upward arch of the road deck completely flattened out. As the steel literally groaned in agony under the immense stress, the road sagged by almost 2 full meters. Now, what's really interesting about this slide is that this terrifying moment, this unbelievable 2-meter sagging of the deck, was actually the ultimate proof of Strauss's sheer genius. The bridge didn't snap, the connections didn't fracture, the towers didn't fail. It bent, it flexed, it breathed, and it absorbed a mathematically impossible amount of kinetic stress. It was the ultimate, undeniable proof of the legendary resilience of an engineering marvel built decades before modern computers even existed.
Forged 89 years ago, the Golden Gate Bridge is way more than just a crossing from point A to point B. It is a monumental leap forward in human civilization. It stands today as a profound, enduring testament to exactly what happens when relentless human willpower, absolute genius mathematics, and raw courage meet the unforgiving, deadly forces of nature. Looking at this towering triumph of steel and concrete, one really has to wonder if an underdog engineer in the 1930s could conquer the deadly Pacific Ocean with little more than slide rules and unyielding bravery. What impossible physical boundaries in our world are just waiting to be broken next? Thank you for watching World Explain. See you in the next video.